Thanks a lot. I'm going to talk about something grapheme-valued, whatever this is. I will explain to you, of course. The main message will be that I'm introducing an example of a Markov chain which moves in the space of finite graphs, and I will explain how to get a limit as n tends to infinity, and the particular point about it, that it will be a diffusion. And work is mainly inspired by one theory, one paper. The theory is the theory of dense graphs converging to graphons, and the paper we were inspired by is due to Siva, Frank, and Adrian. I try. I have a lot to write, so you'll see. So in this paper, Siva and Frank and Adrian, they proposed Markov chains which were relying on models from population genetics, and they showed that if you do the convergence on graphon space, they converge towards a stochastic process which has continuous paths. So therefore, you can consider them as diffusions, provided that they are Markovian, and they came up with a huge range of examples, including resampling and different kinds of selection. And when Frank told me about this paper and we were discussing it, a few questions came up, and this is to show whether the limit is actually strong Markovian, which was not in the paper yet, and also to maybe, if it is a Markov process, write down a generator, give an analytic construction of the limit, and also in this long list of examples the authors provide, there was missing one example in which you actually have a stationary distribution for the limiting process. And what I'm going to do now is to provide you a very simple model, maybe too simple, we will see, but which satisfies all this so that I can use this example as a tool not to explain you the concept of how I would do this, how I would encode my graphs in order to be able to show that you have a diffusion limit, how to analytically characterize the limit in terms of a martingale problem. That's the program, and our model is the following. Tell me if it's still too small. If our graph is finite with a fixed number of vertices, then we have the following dynamics. Something I'm calling poaching. And it does the following, given the ground state, for any two vertices at unit rate, I do the following. I let V prime cut off all its connections and instead let V prime connect with the vertex V and all its neighbors. And to make sure later we get an equilibrium, I'm also allowing for self-employment, which basically means that for any vertex at rate mu larger than 0, but you can also include 0, we have that V cuts off all its connections. So V cuts off all its connections, but that's not get reconnected to anybody else, it's just a singleton now. So you kind of switch the companies, or you decided to be like a freelancer and go on just by yourself. So this is the model, and the question is, the first question you might have is about the long time behavior. What does this Markov chain with a fixed number of vertices do? And the first thing to observe is that after finite time, we will get that our states are actually in a smaller state than the space of all the graphs with n vertices, which I call Gn. I haven't written it. It will be a cluster graph. That means all components are connected. So you can start with something where not all components are cliques or clusters, not connected, but it will not take long until you reach such a state. And once all the connected components are complete graphs, you cannot destroy this property anymore. That is clear. And it follows that if I'm in the complement, clearly I have a transient state. If I'm in the subspace, I'm recurrent. And I can also easily convince myself that the subspace is actually irreducible, because it might happen that you just, everybody cuts off its connections. You start with everybody singleton, and then you can start building the graph you want to reach. Say again?
Question about the model.
You have a question?
Yeah.
Ask, please.
Each particle has exponential clock.
Yes, each particle has an exponential clock. When the clock rings, I mean, each pair of particles has an exponential clock. When it rings, the first one tells the second one, why don't you come to my company? Or my institute is much nicer than the other one, whatsoever. Might happen. Okay, so now that we know that we are irreducible, we know that we have a stationary distribution, a unique stationary distribution. Let me call this by n, depending on n, and then next question, of course, would be, what can we say about this pi n? I give you an example, explain you my notation for equivalence classes. Let's say n is 3, then we have basically, let's say these vertices have names 1, 2, 3. We have the following possibilities, not many, 5 in total. Now we can have this one connected, 1, 2, 3. 2 and 3 is connected, and 1, 2, 3, the missing one is this one. And if you do the calculation with the rates, which is not that hard if the numbers are small, but it stops very fast, then in this example you would find the following probabilities for these graphs. 2 over me plus 1, me plus 2. And of course, these 3 graphs here, they all have the same probability under the stationary distribution. And this is something which, in fact, I would like to point out, that if the stationary distribution will be always the same for 2 graphs, if we know that what I call the size frequency spectrum is the same, and I write it here as I sum over all the components in G and put the delta mass on the size. And if this is the same as I would do exactly the same on the second graph, G prime, then I know that the stationary distribution has the same value. So this one and this one and this one, they all have the same value. I would like to abbreviate this in what follows with G of G, and I call it the size frequency spectrum. Okay, so what we can show, and it took us a while once you have the formula, of course, it's, but even then it's not that simple to calculate. Do the calculation. I'm doing the following. I can start wherever I want. It doesn't have to be a cluster graph yet. And I take a measure nu, which has values in the integers, and puts mass on the numbers 1, 2, 3, 4, and so on. And then the first claim is, if I start in an arbitrary graph and leaves, and I evaluate the frequency, size frequency spectrum of my Markov chain at time t, then this will give me such an integer valued measure nu. and the probability that I get a particular one will converge as t tends to infinity towards n factorial mu times mu plus 1, mu plus n minus 1. Here I have the product j equal 1 to n, mu to the power of mu of j divided by j, mu of j times mu of j factorial. And this is something which I guess some of you might have seen before. This is nothing else than Ewan's sampling formula. Going back to a paper by Ewens from 1972. And the question is, let me call this for the future, P N MID. MID stands for multivariate Ewens distribution. And no, if you wonder why this particular distribution pops up here, then the reason is simply that we did exactly what we were taught by Siva and Frank and Adrian. We based this whole dynamics on the population dynamics model. And the model which we based it on is in the population genetics literature known under the name infinitely many alleles model. And what's basically happening, if you have a mutation in biology, it hits some place in the DNA. The DNA is so long that you never hit the same place, so you never mutate back. So one of these basic, very classical models is that you always, when you mutate towards a totally new type, which you have not seen before. And this is the model which we want to use here. I will call it YTN. And what we do is we introduce a type space which is large enough so whenever you pick uniformly, you see something new. And I have my set V, which now has the interpretation of the set of individuals. And these individuals in population genetics, they carry genetic types, and the population is just a configuration where every individual is assigned a type. And again, if I would like to tell you again what is this Markov chain doing, then assume that currently our population looks like we have YV, V, and V. That's my current population. Then I have resampling, which means for any two individuals, V is not the same as V prime. I say usually V is pushing out V prime from the population and copying its type, but I can also say K V prime will be replaced, not K, it's Y, replaced by YV. And in addition, I have what I call mutation, which gives the limiting diffusion the name. And mutation means that this happens at rate 1, as before. And then I have for any individual at rate mu that YV will be replaced by totally new type. No? Which you can say you draw from the type space uniformly independent of everything which has happened before. And this is linked to the first one, of course, because what you can do if you have given a realization of this population model, you can always put ETN as the set of those subsets which consists of two elements, such that the individual Y carries at time T the same type as the individual Y prime. Now you just connect by an edge everybody who has the same type. That's a very rough rule. What the authors did, and which was much more colorful, that they also allowed to do this with certain probabilities. But for the sake of what I want to illustrate, I do it like this. And then it's not hard to check that YTN, T larger equal N, if I stick with the set as individuals as my vertices and take the set ETN as H set is my poaching plus self-employment model. Okay, and once I have done this, then I actually have to check that the Ewan sampling formula is the invariant distribution under this infinitely many allele model, and that actually gave us the idea what to expect there. On the other hand, we could not find a proof for that, because the way it's usually done is that you build, it's like the growing trees from yesterday. No, you're related to this so-called Chinese restaurant problem. You start from scratch, restaurant is empty, first person comes, takes a table, second person comes, picks a table proportional to how many people are sitting there, or for some reason has to do some Zoom call and picks an empty table, and so on. And then you go up until infinity, and then you would like to know how the population looks like after the first n. But here we fix n and then we rearrange, and still we say that there's a consistency behind, which tells us that also this one has the Ewan sampling formula as invariant distribution. And the proposition we prove here at that point, it's basically saying that if I sum over all my populations configurations, I take the generator of my infinitely many allele model, apply it to a function f, but the function f actually lives on another evaluation of y, where h of y will be the type frequency spectrum that means I have here the sum over all the types which I have currently in my population, and I count how often for how many individuals have this type. And then I see that if I take this generator evaluation and I multiply it with what I call the MED n of y, then I will just see 0, no changes. That means that it's really invariant until this. And I think this was, even so, it's known that these two things are connected. It was still a surprise for us that it holds here even under this rearrangement, and the calculation is a bit tedious to do. So, but anyway, once you have this, what follows is your original proposition, namely this one, because of the link between these two models. So now I'm coming to the second part, to the graph limits. I'm not talking about dynamics yet. I would actually like to know what is the limit of this multivariate Ewan's distribution on the graph space as the number of vertices goes to infinity. And this brings us to the world of graphons, and what we call grapheme. So I guess many of you are very familiar with it, so I try to do it as short as possible, but there are some things in the setup which I like to do slightly different, or it's done by other people as well, but not by all, so that I have to write a bit. So first of all, I'm collecting in G all the finite graphs, and I'm defining an equivalence by saying that two graphs, finite graphs, are equivalent if they exist in isomorphism, phi between them, or more specific, which maps one vertex set into the other. And this, I won't give you the definition if you don't know what the isomorphism is here, but this will be equivalent to saying that our subgraph densities are the same, no matter, the the subgraph density of a graph, capital F, no matter what this F is. That's my equivalence relation. Subgraph densities I might have also seen, but I have not seen it in the talks explicitly. So let me write how we do it. We require injective maps, which map the vertex set of F into the vertex set of G. And of course, it takes mass only if there exists at least one. And if there exists one, then we we take an average over all of them. So we have here the sum, I write it here, over phi in these injective maps, mapping from vertex set F to vertex set G. And then I evaluate just whether for all the edges in F, I'm actually also having an edge in G if I'm taking the image under these injective. Good. So if I have equivalence relations, I also have spaces of equivalence classes, which will be denoted by this equivalence sign. So I guess this notation hopefully is a bit self-explaining. And the first thing to notice, as I said, nothing is difficult here, is obviously the space of finite graphs is not complete if I equip these spaces with the subgraph density convergence. Actually, it doesn't really matter with which convergent I equip it. The space of finite trees can never be complete because if you have an increasing number of vertices, what should be the limit in the space of finite graphs? And this is general abstract nonsense and has not even to do with the theory of graphons. One can show if I have the subgraph density convergence because in the space of equivalence classes, these separate points, that they always have a complete space. I'm adding here in the notation a bar for the completion and an embedding which maps G, these equivalence classes into this one, no? So that every graph is also an element in this completion space, and this completion space in the literature, it's called the space of graphons. And the theory, maybe I don't write everything, goes back to Lovash-Szegedi, 06. There are many more references, but these are the core papers we quote for our claims, Borgs, Chase, Lovash. And last but not least, but most important for my purposes, that's why Rajat Janssen has this very beautiful survey in which he translates everything in the world of a probabilist and measure theoretic person, what I'm going to use. Because what I really would like to do, and this is what Janssen does, I would have the graphons represented by something which reminds me to metric measure spaces, because I'm an expert on working with spaces of metric measure spaces. So my preferred representation of a graphon is the following. Graphon can be represented by such a triple omega tau, mu, and w, where this one is a Polish space, Polish topological space. This one is a probability measure on the Borel sigma field. And this one is what everybody knows as a graphon, namely my measurable symmetric square map. But here mapping from omega to omega into 0, 1. No? And many people know the omega, the particular setting where omega tau is chosen to be the square with the Euclidean topology. And even more people think that one takes the mu as the uniform distribution of 0, 1, but this is a warning, this only works if you are in the limiting graph world, not for the approximating one. And one thing I always like to do is to have state spaces which include everybody, which is unified no matter whether you're a finite graph or not. And this one does it for me. And I can, of course, extend subgraph densities. They are extendable. No? And usually if we work, no? Now think about all our graphs or equivalence classes as such a triple, then we would say that TF of omega tau mu W is the integral over omega. I pick, let's say, I have given F as the graph which has the vertices and edges, and then I would pick for each vertex, I would pick a point in omega independently. But, and this is some extra notation I do when I put this arrow down, that means that I am sampling without repetition. I really want k distinct particles or number of weak distinct particles sampled, and then evaluate this with product over for all the edges in the edge set of F. I would like, maybe I write the F because then it becomes more clear. I would like to evaluate my W XV XV prime. That's it. No? And then the most powerful result is that the space, this complete space is not only complete, but it is also separable and can be equipped with a complete metric, the so-called cut metric, which makes this space compact. If I equip, of course, again, with the convergence of these tau F, or Fs, this is a compact space. No, and compact spaces are very good if you want to look at limiting dynamics later, because we don't get tightness issues or something, at least not serious ones. However, that's what my recall on the graphones is. I would now like to tell you what are the graphemes which we have, and that's just the subspace of graphones, the one on which our world should live. Namely, we are interested for the purpose what I'm doing only in graphones which are not pseudo-random. Now, you know, if you have W constant a half, that is actually in your mind a graph which you can produce by doing Erdős-Rényi graph with P equal a half and so on. But this is a random graph. Of course, you can take a realization and you have something deterministic, but I don't want all this. I want that if I have a limit of deterministic graphs, the limit is also deterministic graph, so has vertices, has adjacency structure, and so on. And therefore, I'm believing here in those objects from that compact space, 0, 1, which have the property that W of omega 1, omega 2 takes only elements in 0 and 1, at least, no? Almost surely, almost everybody. And these appear in the literature, in particular, they appear in work of Svante Jansen as random-free graphones. No? And again, the problem, it's not really a problem, but one has to be aware of this, that this is a nice subspace we want to have, but of course it's not closed. We cannot guarantee this a priori. And the next question I have to answer is, can we have a description of the compact sets in that space? And the result will not be that surprising, but still it's always nice to have answers to this very clear, obvious questions. And so we know that the limits might be random graphs, or best presented by a random graph, or the equivalence class might have these random graphs inside. And how do I know whether something is random or not? In physics, you would measure the entropy of this. And that's what we are doing. We are saying that given I have such an object, omega tau mu and W, I would first of all sample n, capital N points from this one, and that's just a notation. That's the graph spent by a sample of size n. And then what I would do, I would define the entropy, and now it's not. What? I have to, because I want to do there something else, no? But I will try to do as little as possible, just, no? So I'm defining now the entropy of this object clearly is random. But of course, how random it is also tells us about something about the limit. And we know where in a graph all the randomness comes from. It's from the fact whether the edge is there or not. No? And therefore, we allow a little bit of randomness because we are taking averages if we are evaluating the subgraph density, but it should not be of the order of the number of edges. It should be of smaller order. So the idea is the following. First of all, defining this entropy as the sum over, I take all the finite graphs, let's say with n vertices because it should fit to this one. And then I'm evaluating h of the probability g of n v to be this particular graph f, which I have sampled. And h, because I'm talking about entropy, is of course nothing else than h minus x log x. And then it's a very simple manipulation of terms to see and convince yourself that this is h of the subgraph density of my entropy. The function? This one. You cannot see it's minus x times logarithm x because it is. No, I'm sorry, I couldn't see that you couldn't see. Because I didn't know what was behind me. No? That's the classical one. The mu, you should think about the sampling measure. On the state space omega. No? And you should actually, if you're a little bit familiar with the spaces of metric measure spaces or sampling convergences, the way I have written this is already in the way that you see that you have a sampling convergence, you sample, and then you evaluate your object. And you evaluate by the structure it is inherent, and here it's of course the function W, which is the important one. Okay. So I already said what we want. We want that the entropy is not zero, but smaller order than the number of edges. In that case, n over 2. And if I have a whole sequence or whole family of objects, then of course I have to have this property uniformly over all the graphs in gamma. That means that I'm now saying I would like to have, say that the subset gamma of these objects 0, 1 is relatively compact. If and only if for any delta positive, I can find a large enough n such that the entropy evaluated at the density of this object is smaller than delta times n over 2. And uniformly means I do this for all the omega tau mu w which are in my space gamma. Yes?
Just to clarify, so you wrote there that we have UPF. Are we still taking the sum there? So you said, oh, this is
Yes, a sum.
Yeah, the next slide. Are we still taking the sum there because there's an f there? So it's the h of the tf of w. So I guess we're still taking the sum over all f, right? Yeah. Okay. No, just. Yeah. Okay. Thanks.
Thank you very much. Same here. No? Sum over all the f. Yes, so that's the criterion. I think I made a bit clear why this is the criterion you should have. And what we do in order to get closer to what I want to do, we apply this now with which gamma? Of course, we will apply it with, no, it's not clear with which one, but I'm telling you, something I call okay, if I would apply it to this one, then the answer would be wrong because we know it's not closed. But I'm restricting to cluster graphs. That means ADUs, where all these connected components are complete. I have not told you what it means in the limit setup. I will do this here. These are just all the omega, tau, mu, w in the space for which we have the following property, namely such that for all, whenever I pick 3 points in omega, almost all omega 1, omega 2, omega 3, I want to have this property that if omega 1, omega 2 is 1, these two are connected, and omega 2, omega 3 is 1, that means these two are connected, then I also would like to have that omega 1 and omega 3 is 1. No? And whenever this holds, these are these diagonal, block diagonal graphons. If you think about the square maps, then you have complete graph components. And what we can conclude from this criterion, if we do the calculation, is that the space which I have just introduced, cluster graphs, so here our situation, it's really trivial, that this is relatively compact, that it's also closed, and therefore, as a closed subset of something compact, even compact. And from this one, I can immediately conclude that my multivariate Ewan sampling distribution on the space of graphs of size n or equivalence classes of them converges weakly towards a limiting probability measure, and the population genetics literature tells us even what it is. Because a lot is known about these equilibrium distributions in the context of mutation, and I can represent the limiting one, which I call, GEM, it's called, Griffiths, Eggins, and McCarthy, I think it's his name. And the representation is that you take better random variables with 1 mu in an IID fashion, then you can say that a graph is connected to GEM, distributed like GEM, if the size frequency spectrum is given by the sum I larger or equal than 1 delta of Vi times the product 1 minus Vj. J runs from 1 to I minus 1. No? So that tells me that before I've even started to look at dynamics, that our Markov chain has an equilibrium distribution, and this one converges and has a limit on the limiting space, which lives on graphons which only take value 0 or 1, or can be considered as graphs with a measure on it. No? Because you can sample from that graph. Has countably many vertices, you can sample from that graph. And graph with a measure was actually the idea behind to call this grapheme. No, that's graph is a measure was our idea. Many things are flirting around. So now we come to the grapheme-valued dynamics. In the limit, should be limit dynamic, type limit diffusion. And here we will rely on two facts. Now the first one is consistency. That's what I was asking about all the time. Because whenever you have this, you can start thinking about whether you can up with nice dynamics, which you might be able to construct limit dynamics for. So the idea is that if I run my Markov chain with n vertices, but observe only a sample or the subgraph spent by a sample of size k, then what I see is actually my Markov chain as if I would have to begin with at only these k vertices. It's more a projective property than a consistency property. And that's what we want to make use of. And the second one, which is inherent in our choice of the topology or the notion of convergence, is that the subgraph densities, they are continuous. They induce our topology, but even more, they are convergence determining effect, which I had to drop here. One has to show, of course. Also, no? And that means that all our generator, that all we have to do if we want to construct the limiting dynamics in an analytic way is to come up with a uniform convergence of the generators. Because for tightness, usually you need that nothing can happen in small times, but if generators converge uniformly, you exclude it, that it cannot explode, but our state space is compact, it cannot explode. No? And as for the generators, I have not dared to write down any, and I will also not do because it's too much notation, but I try to convince you that if I apply the generator for the poaching with self-employment model, on a graph with n vertices to our densities, and this is enough to apply it to these subgraph densities because of this second point. Then what I will see is that my generator has a linear form. It will basically be f again will be here. I'm sampling not k points, but for each vertex in F, I sample a point without repetition. And then the density itself here had the product over all the requirements that the edges which are in F should be also edges in the corresponding edges in G. And here we see that since everything is linear, actually the generator action acts only on this one, and it acts only as my generator on the graph, which has the number of edges as F has, and all we need to do is apply this generator to an indicator function which acts on the adjacency matrix of F and evaluates the adjacency matrix of X and just checks whether both adjacencies are the same. And here we have, it's not exactly this one because I work here with adjacency matrices, but of course you can imagine that there's a one-to-one correspondence of a finite graph and an adjacency matrix. I don't want to introduce all this notation here, but this is what you can do. This is how this generator looks like, and the main and only message I want you to take from this is that it has this algebraic structure and that the right-hand side does not depend on n. Explicitly, of course. I mean, if you sample from n without repetition, it's different than if you would sample from something else, but the expression is the same. And that means I could also take this for my limiting generator. And this I call Wright-Fisher plus mutation. I can take exactly the same expression. This acts at tau f of omega tau mu and w as this one does, as the right-hand side here. And then it's very easy to show that you have uniform convergence of the generators. And maybe I have not much more time. Maybe I write one more, or not one more, but I write the main theorem. The main theorem tells us the following. There exists a unique Markov process, or there exists a strong Markov process, continuous path, values in that space of graphemes such that for all F finite graphs or their equivalence classes, we have that if I take the density of my if I let run my, no, that's the limiting diffusion. If I take in this diffusion, which is graphene-valued or grapheme-valued, the subgraph density at time t, and I subtract the accumulated changes, which are given by applying this generator to the subgraph density and plugging in xs, dxs, that this is a martingale. A martingale, no? So there's exactly one process which does this for us, and this usually defines your Markov process uniquely. There's one more statement which we can do, and that is that for all initial graphs, G0, and they don't need to have complete components, doesn't have to be a cluster graph to begin with. We have that the law, once started in G0 of this diffusion, because it has continuous paths, converges to a GAM graphon as t tends to infinity. So that is the statement. This gives us a diffusion. I have not told you anything about how we get uniqueness, because that would be more than an hour, I guess, to do this, because then I needed to write down all these generator expressions explicitly and write down the duality we found on the level of. But the moral is that it has a dual, and the dual is actually the finite graph object, but encoded as adjacency matrix valued object. And it's not a real dual, it's a Feynman-Katch dual, but Feynman-Katch dual, it's enough for checking the uniqueness here. And say again?
What does it mean,
Feynman-Katch dual means that it's not, you know what is a duality relation? That you have an exponential term there, which refers to the fact that yeah, you might jump to infinity and then dual picture, something gets inserted. We rely on the fact, and that's also something I cannot talk about here, but it's very nice. I always try to do advertisement for this. If you have a finite state Markov chain, you always get a Feynman-Katch dual if you just turn around the time. If you turn around the time or exchange the rates, not take the forward rate as the backward rate, but then you always have a discrepancy in the rates in each point, and that's your potential which goes in the Feynman-Katch dual. But you can always get like out of the box a duality relation, which might not be useful if you want to study it, but it might be very useful if you want to prove uniqueness with it. And that's what we did here. And as for challenges, I told you that's not the most difficult model you might have in mind. I'm sitting here and looking for nice models I would like, no, dynamics on graphs or graphones I would like to pick from you. And it's also only in this dense setup, but you can do it also sparse, because nobody tells me that I have to take the measure, maybe a probability measure. I can go to something more general, like locally boundedly finite and so on. But this is the first piece of work we did in that direction, and that's what I presented today.
So I'm wondering, so I mean, I completely understand that if you're looking for characterization of your complex sets, right, and your topology is generated by subgraph counts, right, that you define, define an entropy of subgraph counts. Could you say something about how this relates maybe to the sort of the Shannon entropy of these finite, because that's at least for me, that's an entropy of finite graphs and graphs that I know.
I'm not so familiar. I mean, I know that it has to do with relative entropy or something, but I don't know how to relate this in this particular setup. In this particular setup, I have a random variable. I want to know how much information is there. And I can do this with this functional. And that's all I needed here. I have not thought about how this is related to them. For that, I also need to learn more about these concepts there.
So what do you take when you build a background?
Mm-hmm.
That's 0, 1.
Are there models for which you have an equivalent measure?
I mean, I could in my, I see. That's, I don't have any, but I would like to have one. This one is not an example of it, no?
So somehow you need this mu to sort of play a role.
No, the problem here is that actually my limits are just countably graphs. That I have really atoms, no? That's why I can write down the weights of these atoms in terms of this gem distribution. But there should be other dynamics also, but usually, as I know from the tree world, that it's always harder to get. It's also in population genetics. We have the Fleming-View diffusion, but you know, if you look back a little bit in time, you only have countably many ancestors, and that's what comes in here.
If not, then